Throughout our history, threats and challenges to humankind have often been overcome by periods of genius. Today, knowledge is shared like never before, and bonds between innovators grow stronger, crossing oceans and dissolving borders. The trouble is, we need energy to power our world, but today's energy sources carry a very heavy price, polluting our atmosphere and dangerously heating our planet. Fortunately, a variety of companies, from plucky startups to global megacorporations, are working together on clean, new and sustainable energy solutions, placing our world once again on the cusp of incredible rebirth and revival. From a gentle breeze to gale-force wind, the air that moves throughout our planet's atmosphere is a perpetual source of natural energy. But wind is a complicated force, and harnessing its power is far from straightforward. Available land for wind farms is at a premium, and until recently, deep water wind farms have proven too costly to set up or maintain. Which means that the largest wind energy resource on the planet, the powerful winds further out to sea, remains untapped. X1 Wind is developing an innovative solution: fixed, offshore, floating wind platforms. With reduced weight, lower installation and maintenance costs, and fewer constraints on depth, X1 Wind is making floating wind turbines a competitive source of clean energy.
Now it's actually the cheapest form of electricity generation, if you choose a good site.
Carlos Casanovas' career has taken him across the globe in pursuit of offshore engineering solutions. He's had the privilege of working on groundbreaking technology with some of the offshore industry's biggest players. So when most people think of wind turbines, they think of these fixed turbines on land. So clearly you're breaking the mold. What are the advantages of going offshore, and second, of making the platforms floating?
Yeah, just for going offshore, the immediate advantage is more wind speed. So you get more energy out of the wind, the faster it is. And the further off the coast you go, the more wind speed you get too, which is the reason eventually floating makes sense. Fixed, you can only do it in shallow water, and most countries are not that lucky.
How much deeper does a floating wind turbine allow you to go?
With a traditional mooring system, which would be a catenary type mooring system, you can easily go up to 150 or 200 meters before you start having some issues. What we propose is a bit different, which is a TLP type system, which has 3 vertical lines connected to the platform. This is also used for oil and gas platforms, and they can go as deep as 2,000 meters, so the possibility is there.
How exactly do we get that energy back to land?
Yeah, so these things have an electrical cable coming down of them, and you just connect all the way to a substation inland and connect to the main grid. So you need to have a substation reasonably nearby, otherwise you have a lot of losses in the cable.
And what are some of the challenges in developing this?
So we are in the crossing of the turbine itself, which we need to understand, and we need to design for it and simulate accounting for the presence of the turbine. Then just working in the ocean environment, all the operational aspect, how you install this, how you maintain.
And so what's the next step? How do you see yourself progressing this technology?
We want to be building a full-scale prototype, right? So something with a turbine that can produce upwards of 5 megawatts of power, because this type of floating system has many innovations. So we want, let's say, 15 megawatt, which is the next milestone of the industry. those are 200, 240 meter diameter with hub heights which are 140, 150 meters high. So it's going to be massive compared to this. This will look like a toy if you put them side by side.
I mean, that sounds
Sure.
huge. What is the advantage of making them bigger? Does that allow it to generate more power?
Yeah, because the power is a function of the area swept by the rotor. So by making the blades longer, it's a very efficient way of extracting more power without having more units. Also then the blade reaches higher. The higher you are, the higher the wind speed too. So
Yeah. How well do these handle massive storms out to sea?
well, they have to be designed to handle them. So you're forced to design for what they call a 50-year return storm. So it's the worst storm you may have in 50 years. We use several simulation tools. Ansys is the one we use for structural design. So I'd say structural is where we spend most of our time.
This is one example of our simulations. This is the whole platform that we design. This would be an example of the whole system being tested for the loadout. That would be the operation in which we lifted the whole platform and put it into the water.
Maria Vergés is an industrial engineer who has been with X1 Wind since the beginning. She oversees design planning and the technical side of the business. So what am I seeing here?
In here we're seeing a check for buckling of the members. Since we have very long, slender members, this is a very failure mode that we could have. So in here it's a specific buckling check. So that's one of the main benefits of simulation. Like you can see how far can you go or how much can you optimize.
Multi-physics simulation gives us the ability to explore and predict how products will work or won't work in the real world. It's like being able to see into the future, enabling you to innovate as never before.
It's the standard way of doing it, so that's why certification bodies, they believe directly the outputs of the software. So we prove with this that the platform works and it's safe and we're using the proper loads and safety factors and everything.
Hydrogen. It's an abundant, clean fuel which can be produced from a variety of sources, like natural gas and even solar. In fact, it's so clean that when consumed in a fuel cell, for example, the only waste produced is water. But it's also a highly volatile, flammable gas, which makes harvesting and handling it a very difficult task. One company rising to the challenge is Baker Hughes, an energy technology company with a diverse portfolio spanning the global energy landscape. As part of their mission to take energy forward, they are accelerating hydrogen deployment as an alternative source of energy.
Efficiency is a direct proxy for carbon emission in reality, but it's also it's a competitive requirement.
Rod Christie is the Executive Vice President of Turbo Machinery and Process Solutions at Baker Hughes. Since January 2016, he led one of the industry's most comprehensive equipment and service providers for mechanical drive, compression, power generation, and transmission solutions across all oil and gas segments and the industrial sector.
We really look at how do we drive the efficiency, reliability, the availability. So how do we maximize the performance of the asset that we sell?
So in an ideal world, if everything could go perfectly and you could create the perfect plan, what would be the near-term kind of steps we have to achieve to get to that perfect future where we've decarbonised?
So we should have started 10 years ago.
Of course.
A mid-term vision of carbon, and we talk carbon dioxide. Obviously, there's methane emission, there's hydrogen emission. All the forms at which you create climate change, you create heating content in the atmosphere to make the world hotter. What's the cost of emitting those? What do I need to do to take it out? So how do I avoid that cost and do the right thing?
I know that one of the main or one of the big parts of your climate tech is looking at hydrogen.
Correct.
So tell me, why use hydrogen?
The application really is around obviously hydrogen combustion in reality, and then the fact that as you combust hydrogen, obviously for heat or for power or for a variety of different things, it's a very clean fuel in its burn. There's no carbon entrained in the hydrogen itself, and obviously one of the things that is part of the challenge is getting carbon and carbon-related emissions out of the atmosphere.
So earlier I was walking around this compound and I saw a lot of really cool looking kit, and it all looked quite complex. So perhaps you could tell me what exactly you're making here and how you go about making it.
Certainly. Embedded through all of our facility, we have a lot of innovation laboratories, and in those we'll test out early technology, whether that is things like 3D printing, additive manufacturing. So how would we take metal and print components and prove that they are suitable for the application they're in? You know, a big piece of what we do as an energy technology company is really innovate and think about technology today and technology of the future. And it starts really in the engineering operation, in the offices of the engineering team, working with advanced simulation tools, really to take the concepts and ideas and model them in the computer and then run them as if they were running in real life. And from that, tune the idea of, you know, what are we going to make, how are we going to make it? And then we'll take that concept and then manufacture it at smaller scale and test it and make sure it does in real life do what we see in the simulation. That allows us to move much quicker. So the simulation and then the testing here in the laboratories, the innovation centres that we have, allows us really to bring technology into the marketplace at a faster rate. And the additive manufacturing capability, the printing capability that we have, allows us to print very, very complex organic shapes that allow us to manage fluid and gas flow in ways that we weren't able to before. So it's opened up the capabilities for both the manufacturing team and the design teams to make things that we thought weren't possible 10 years ago.
As someone who's very much leading the charge in this industry, are you optimistic about our prospects of getting carbon neutral?
I think from a technology perspective, I'm going to say yes. From a policy and regulatory point of view and a speed of change, less so. Basically, at a global level, the geopolitics of carbon cost and carbon management is really complex. To move forward, we've got to, as industry, we've got to really look at, are we doing the right thing and how do we change it? And then I think you'll find that as more pilots come in, as technology matures, it gets easier for governments to regulate because the framework and the requirement starts to narrow. It's less of a broad field, it's less of an unknown. You start to narrow that in. The government has a very early part to play with, this is not acceptable. Industry, you need to go find some solutions. And then I think as industry finds solutions, it's much easier then for them to regulate around.
Sure, and this might be putting you on the spot a bit because I understand it's very hard to sort of project into the future. But if you had to guess, what kind of percentage in a completely decarbonised world would you expect hydrogen to give our energy sector?
So I'm going to project quite a long way out. I would say, so you're thinking sort of 2050 and beyond. Hydrogen, I think, will grow and be a 20-30% mix potentially, or clean fuels will be a 20 to 30%.
That's fuels rather than energy.
Yeah,
right.
And then it'll decline as we shift to other areas. The big swinger in all of this longer term would be things like nuclear fusion. It's in a 25 plus year time frame. So if you project out to sort of 2050, where you think of all the nuclear fusion technologies are today, they're sort of saying by 2040, 2050, we would like to try and get into a commercial application. But likewise, you'll see that by then you'll have a lot more wind, a lot more solar, tidal, more hydro build out, clean fuels, carbon capture, hydrogen plays. It'll be quite a mix in reality.
As the demand for clean, carbon-free energy grows, fusion presents a unique opportunity. The same process that powers the sun, it combines the nuclei of lighter elements like hydrogen to form heavier elements like helium, releasing colossal amounts of energy in the process. We know that it's possible. Sunlight is the proof. But can we make it happen down here on Earth in a safe and economical way? Well, let's hope so, because humanity's future just might depend on it. Scientists have dreamed of fusion power for decades. Now, general fusion is closer than ever to making this emission-free energy source a reality, accelerating our journey towards clean, carbon-free electricity.
Fusion is the holy grail of energy. We're talking about a fuel source that is really derived from seawater. It's clean, it cannot be weaponized, and it's safe.
Greg Twinney joined General Fusion in 2020 with a well-established track record of executive leadership. He has expanded the company's investor base and helped to launch the Fusion demonstration program.
My job is to ensure that we commercialize fusion energy. It is something that the world has been chasing for many, many decades. And finally, with all of the work that's gone into plasma science, computing power, 3D printing, simulation, all of those things now combine to actually take them off the shelf and turn them into reality.
Awesome. So how do you commercialize fusion? What's your roadmap?
The goal of our activities so far has been to progress the science and technology to a stage where we can feel confident that pulling it all together and demonstrating at scale that this technology is going to generate fusion conditions that are economical and in a timeline that matters to cleaning the energy grids.
There is no doubt that numerical simulation has a very big role behind the development and the progress in fusion energy.
Fusion has long been a passion of John Sebastian, and his interest in General Fusion's magnetized target fusion technology pulled him away from the aerospace industry. Here at General Fusion, he uses numerical modeling to bring fusion closer to commercialization.
So scientists have been talking about fusion for decades. Why is now different?
What would take about 2 or 3 months to run a decade ago on a computer cluster now only takes a matter of days, which allows us to really iterate and design at a much faster pace. Our technology uses liquid metal to absorb fusion energy, and fusion energy heats up the liquid metal, and this heat can be extracted through a heat exchanger to create vapor, steam, and this steam can then drive a turbine and produce electricity. And numerical simulation has allowed us to confirm this objective on our latest compression system prototype. And this achievement is able to really confirm the feasibility and practicality of our technology.
One of the biggest problems with plasma physics is as you compress this thing, you have 150 million degrees C here, and you have room temperature here. So there's a huge gradient of heat, and that tends to make turbulence. So the plasma doesn't want to stay still, it boil. And
Part inventor, designer, and physicist, Michel has a wealth of practical experience in plasma physics and modern plasma diagnostic techniques. He has extensive knowledge of the latest technologies and is experienced in designing and constructing test apparatuses to evaluate technical concepts.
we're trying to compress the plasma with liquid metal. And there's a bunch of piston driving by steam that will push on the liquid and implode it. But it has to be round. If it's not round, it's going to go whoop, 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 like this, and it's not going to work. So you need a good synchronization of all the pusher to push that in a nice circular thing. So this is a machine that's working on that. We have 28 pistons around here, and we control it with all sorts of fancy electronic. And then we look with a camera at the liquid coming in, and we see if it's nice and round. And at peak compression, the variation of height is about 10% of the radius, which is what we need. So it's 10% fluctuation around the circle there. So we achieved that. We're very happy. But this is only one layer. The real machine will have to have many layers in order to implode we want to fire the top and the bottom first to implode like this to catch the plasma in the middle. And that's where this machine comes into thing.
Each of these is an individual piston.
Yes, each of this. So the compressed air goes here, there's a piston here that goes compress the gas in front. This rotor over there goes in the middle here, and it spins. The water's against the wall, and then we fire all this, and then the piston goes whoop, and the fluid implode nicely. But if you don't have enough layer, then you cannot carve the curve you want. You know, if you have 3 only, it won't make a nice curve. So 7 seems to be the curve that we've decided on. And this is from simulation, like we simulate it with 10, 11, 10, 7, 6, 5, and we need to make a nice liquid that implodes nicely. If there's not enough layer, you cannot make the nice implosion happening.
Our current trajectory of demonstration will allow us to demonstrate at scale that the economics are competitive with coal. When you think about in the world where the most coal plants are being built, India, China, we need to be competitive with those forms of power generation, or we just will not achieve our long-term targets of helping the grid decarbonize.
And so what are some of the considerations you've got to take into account, kind of in the big picture of making it commercially viable?
We can't solve fusion on our own. We use partners. We use external national labs to pull together all the knowledge that has been generated around fusion over these decades to create our solution for bringing fusion to market commercially.
No one is doing this alone. If we are to achieve carbon neutral energy, it's going to take big, game-changing ideas to get us there. Lots of them. It takes people to champion those ideas. Innovators, inventors, disruptors, and leaders. And it takes the right mix of tools and technology, granting us the uncanny ability to see into the future and innovate as never before. This is the greatest rescue mission of our time. We are the source of our new energy, and the planet is depending on us.